Good afternoon, YouTubers, and today we're going to be discussing how to do kind of I would say, heavy math within an Arduino environment. And you will say, why an Arduino? Yeah, Arduino is not for controlling parts, controlling something, turn on a pump, turn on a switch, do something, physical, basically. And the answer is yes, but it can do more than that. And basically what I'm saying is you can use Arduino to program to do many things. And one of those is, for example, you have a cubic equation like this one. It's a polynomial with x to the cube b times x to cx plus d. So it's a polynomial you have, and where a, b, c, and d are well defined. Yeah, they are numbers. Those are numbers. And basically, if you follow this procedure within the Arduino, when you are programming the Arduino, you will come out with the answers. And the answers will depend of whether some particular delta value here calculated, whether that value is either positive, equal to 0, or less than 0. So you have to take a decision. And that's where the Arduino also come handy, because with the instruction if, you will be able to evaluate everything that is required here. So just to make a story short, basically the first thing that you want to do is I'm gonna show you here in parallel. Let's see if I can close this a little bit. And here is what I have. It's the solution of a cubic equation, and I have many examples here, like 6x to the cube, 29x to the square, 36 plus 9. That's an example where the roots are all different. This is an example in where at least two roots are equal. And there's a story with that behind of what you have right here. Like, for example, it clearly said this is the Spanish version. I looked for the English version, but it wasn't as clear on the setup of what to do to resolve it. So I end up using this one on the Spanish version of Wikipedia. And I tested. Basically, it says, particularly here, if the delta is equal 0, you will end up like with two imaginary roots. And that's basically what this example will do for us. So depending of what your constant are, so that will produce a different value here with the delta. You will have a different value, and that delta need to be tested for what of these three rows it will fit. So A, B, C, D, value of delta. You start to define all the variables that you need, like for example PQ, VU, they're right here, V and U. And now you have theta. Theta is basically this guy here, which is arccosine. Can Arduino do that? Oh yes, it can. You need to look for what is the arccosine definition for Arduino. Now, a couple caveat here that you have to be very, very careful. Depending, for example, these roots here, 1/3 or root, these roots, you have to be careful. They are to the 1/3 right here. And those roots, it might be that all these here might be negative. If they are negative, you have to be careful with the POW instruction, because we know that the result must be negative. If this is negative, the 1/3 root will provide a negative value, but Arduino will not be able to calculate that, because you have to change a little bit the concept and make it positive first, so the POW will not fail to you, and then you know that it has to be negative, then you put them negative. It's a trick. You have to do a little trick to be able to calculate here. I think that these are the most where you might have a little bit of a trouble to do this, but it's straightforward. Everything else is just you define the constant. And here you can see I got x1, x2, x3, but I also have the real part, and I call it x2r and x2i. And you might say, where's sometimes for that you want to use x1, x2r, and x2i, and they will repeat itself, except that they change from positive to negative. So that's why you don't see here an x3i, because it's the same. It just change the sign here, plus and minus. That's basically it. Now here's where the calculations start. You want to write things to the Arduino, so your monitor, serial monitor, so you start with the serial begin 9600 baud rate. Now the P is basically what I have here, 3a times c minus b squared, b times b, over parentheses 3a squared, the next one is q, equal 2, exactly like I have here, 2b to the q, so 2 times b times b times b minus 9. You can use power here, POW, but I rather not. And I rather not because maybe b is a negative value. If b is a negative value, POW will fail. So you want to be careful with that. Minus, so I keep everything, like a squared, d times d, all that parentheses divided by 27 times a times a times a. That will do. Now, with that P and Q calculate, you calculate delta. Delta is this here. It says that it's going to be Q squared divided by 4, P plus P to the Q divided by 27. And now we're going to print that value. We're going to call it delta, obviously delta, and then we print that value here, delta. Now, here's where we start to make some of the decision. If that value, in this case, less than 0, there's something here. It says if delta is less than 0, you can follow this x1, x2, and x3, and you have 3 real solutions. When delta is less than 0, it clearly said here you're going to have 3 roots, and they are all real and different. For delta, for that particular case, that delta is less than 0. And the first thing that I got to calculate is something called theta. Theta here is called 3q over 2p, but that's the arc cosine. This is the argument. That's the argument. So theta here is 3 a cosine, parentheses 3 times q divided by 2 divided by p. That's actually where we are here. 3 times q divided by 2 divided by p. Now I got the POW, and here we go. Why we are here is very interesting. Basically, that POW, which is here, minus 3 over p, that p is negative, guaranteed. Under this circumstance, p is going to be negative. P negative, with this negative, I can calculate this POW, no problem. That's what's happening here. P is negative. When delta is less than 0, that P is going to be negative. No question asked. And that will cancel out with this negative. Eventually, you can calculate the POW, which is the power, right? That's basically what I'm doing is the square root. That's why I have 0.5 here. So I calculate theta. The next thing is to calculate x1, x2, x3, following what is have here. So it's 2 times POW, that's for the square root of minus p over 3, the comma of 5, because that's for the square root, time the cosine of theta over 3, that's this first one, so that's all one number, minus b over 3 over a, that's b over 3 over a, that's this part here. So you calculate x1. For x2, you do the same. Nothing changed. Basically, it's a copy of the above, except that now inside the cosine, you have this calculation here. 2 times pi, and all that divided by 3. As shown here, also here, and here. Minus b over 3 over a, that's this last part. And for x3, we do the same. 2 times, the only thing that changed here, that is here it clearly says that's theta plus 4 times pi, parentheses, everything divided by 3. That's actually here. And minus b divided by 3 divided by 8. So we calculate x1, x2, x3, and with that, we calculate, we send to print a few things here, like for example, silver print the angle theta and the value x1, which is x1 here with 4 decimal place, x2 4 decimal place, x3, and so forth. So this basically this if delta less than 0, this take care of all this part here. Now if delta equals 0, it says when it's 0, something that all roots are real and 2 of them are equal. That's the particular case of theta equals 0. Now for that particular case, I used pretty much everything from here. I'm only going through what is here, but basically less or equal 0 is the same. You use the same equation. In fact, all this part here are identical to this part here. All right, the only thing that I did kind of a different, I separate, if anything, was because of the discrimination here about what to do, and I just write it, but the equations are the same. So these will apply for both cases, either delta equals 0 like this one, or delta less than 0. So you apply that the same. End of the story. Now when things change a little bit, well, a lot I would say, when delta is greater than 0. Now for delta greater than 0, you have to use this part here. Okay, and that particular case, when delta is greater than 0, you have to do a few things here and there, and one of them is start here. It says delta equal POW. Let's see where we are. We are taking this square root here. That's the first thing that we are doing. We're taking the square root there, and now we are calling this argument here. That argument is called minus q over 2 plus delta. But that delta here, remember I took, let me fix a few things here and there. Oh, I got an error here. Let me get this right. There we go. Delta. So delta equal POW delta, and that will do. So now we have, so we took the square root of delta here, and as I save it back again in delta, and now I am adding that here, minus q over 2 plus delta. So basically minus q over 2 plus that delta has already the square root, so that's why it's there. Now for the other argument, I have minus q over 2 minus delta. That's this one here. So, and now you calculate u and v, and this is very interesting. Here's where the problem might start. You gotta be careful with this POW. If it just happened that these arguments are negative for any reason, u and v they will not be calculated. They will not. This POW will fail if this partial 1 or partial 2 are negative. POW will fail to do that. So this is the part that is required to check for that, and I do it after this, because if they are positive, no problem, but if they are negative, I have to check that part here. So this argument here, what I'm saying is, if this argument is negative, you have to be careful. That's what I'm saying. All right, because if this argument is negative, this POW will not work, because this POW is the 1/3, 1 over 3 basically is 1/3, or you can put here like 0.03333, so 1/3 root, and here as well, because I'm doing this. What is here is here, but it will work if the inside here is positive. I can, it would be, well, it depends on the sign of Q and here. If Q is, one of them will be negative, one will be positive, probably. but the issue is that you don't know which, and you gotta check it here, and this is where you check for that negative sign. If partial is less than 0, you get here, and you do this trick, you get the absolute value. Now partial is a positive, and now you can calculate the u value, no problem. Remember, what it will happen here, you're gonna get the square, in this case the 1/3 root of this number that is here. It's a positive number, but you have to remember that it must be a negative eventually. Remember, it's like as an example here, it's like you are trying to do this as an example, POW of something like minus 27, and you are doing the 1/3, so let's say 0.333. The answer of that in a regular calculator should be -3. So -3 to the third power should be 27, -27. But POW will fail as soon as it sees a negative value here. So that's the problem. That's why before doing anything else, before calculating the POW instruction, I want to ensure that partial 1, which is the argument, one argument, like here, is a positive value by doing this. All right, but now I know that the result eventually is going to be negative, like shown here, so I put a -u. I also check the other argument. If that's less than 0, I'm talking about this one here. If all that is less than 0, I make it positive, do the trick, and come back. Check that I'm putting 1/3. Remember, be careful. If you put something like this, 1/3, Arduino will think that you are doing integers, math or integer math. Integer math, that's a 0. 1/3, there's no decimal places, and you will screw up. So that has to have at least somebody had a 0, a dot there. And I like to put in both sides, or put 0.333 like I did here, like this, no problem. And that will do, and B end up being negative. Now that I had that, it's as simple as doing all this here, and x1, what is x1? Is u plus b minus b over 3a, over b over 3 over a, right there. So x1, no problem. Now, this part here and this part here are identical. They are identical. That's why you see here only one calculation and this is called x2r. X2r is just the real part. Since they are identical, there's no change in anything. Basically, it's better to calculate the way it is here. It says -1/2. Check again that I put the zeros there, 1.0, 2.0. Don't allow 1/2 without, because that will be interpreted as integer math, times u plus b minus b over 3 over a. That will do. Now, for the imaginary part, which is this part here, I have the square root of 3, you see, over 2, no problem there, times u minus b, and that particular case is identical here, except that one is positive and the one is negative. But that's the imaginary part. Then the only thing that I have to do is print this the way it will look like this. So there's a real part, and the first thing I do is print x1. I print it, then print x2. But for x2, this is the real part. I'm printing the real part, and then a sign, a plus sign, and now I'm printing the imaginary part, the x2i with 4 decimal places. See, and then I print the I. So this is the I there. Now, for the third root, what we need to do is the same. x3 equal. Now we print again the real part, but now their sign is negative. And now we print the imaginary part, which is identical to the one at the top, and then we print the I. And that's basically, my folks, we have completed this run, which basically is the conversion of everything that is here into Arduino math, in case that you need to solve a cubic equation for his roots, either imaginary root or real root. Let's test this one. Let's see. Let's open this big, and as you can see, I'm doing this. I'm doing all this within Tinkercad. I'm using why close. So we are ready for testing. Let's test this guy. So I got a 2, 5 right here, 5, a 6, and a 30. And it says clear here that we're gonna get oscillation, and it's a unstable system. And let's run. Let's see what we'll do. There we go. There we go. Here we have the results. We have the delta value is a positive. So there's an expectation according to, let's see where I have it here. I can look that, okay, right here. According to, if delta is greater than 0, there's going to be 1 real root and 2 will be complex. Good. So now let's go back to my friend here, Arduino. I'm running Arduino here from Tinkercad. Just make life easier for a second, but this code will work okay in the real Arduino as well. No big deal. Actually, this is Arduino Uno. And the important thing here is that I calculate the roots. X1 is that's the real root, minus 3.09, but the imaginary root is right here, and that's why I have this here. For this example, this will provoke oscillation, but they're gonna be growing as we go. And if this polynomial were, like for example in process control, that would be a problem. So this is not it's not providing a system that can be controlled the way it is right now. All right, now you can test for another one. Like for example, I can check what's gonna happen if I set this. Actually, this is the different, the same. This is the same, but I can change something here. Let's say, for example, let's say that this is 15. We're gonna change that. Stop simulation. We're gonna change that and see what happens with if I put it. If I set that D to 15. We clear the result, previous result, and we run again, start simulation. And now I can see clearly there's another issue is popping up. Very interesting. Let's see if I can open this a little bit more. No, I can't. So delta is still positive. My first root, x1, as shown here, is negative. It's a real root, no problem. But this one, the real part is 0. But it's oscillating. In other words, this polynomial that I already put together here, like 2, 5, 6, and 15, I can write this down and change this. Instead of leave it 30 there, let's say 15. If I remember that right. Now that's I will say it is a stable system. Yes, it is a stable, but it's a critical stable. Critical stable. That would be the answer for this one, because there's the real part is 0 on the imaginary part, but then the system will oscillate forever. All right, so that's what it means. So in other words, if this polynomial show up in something you're doing in process control, the system will oscillate forever. It's critical. The oscillation are critical. That's what they call it. Now, if I use the first case, this case here, it clearly says that all roots are different. So let's see, 6 on the first one, 29 here, 36 and 9. Let's clear this. If I run that one, start simulation, you see all roots are negative, meaning that this is it's the case where delta is less than 0 right here, and this is theta, and all values of the root are negative, meaning that this polynomial, again in process control, that would be a very stable system. That's what it said. All right, so I think that we get pretty much what we intend to do. That yes, the Arduino is enough to do kind of a, I would say, complicated math, you know, as long as you don't get run out of memory, everything should work okay. And basically what I did is to work out all this equation in a particular order, and the only part that you have to be very careful is with the POW. It works okay, but if you ask to get a negative value, that would be a problem. Like for example, and with this I'm done. I just want to stress the fact that be careful when you are working with a cubic. And like for example, let's bring here this, let's see, I'm going to create a new circuit, and I'm going to bring an Arduino again. I'd like to rotate this a little bit. Now get to the code. We're going to delete all these because I'm not going to be using that code at all, and we're going to delete this as well. So we're going to have that void set up there, and this is what I'm saying. If you want to, like for example, I want to print things again to the serial monitor, so serial begin, I want to set that up at a baud rate on 9600. That will do. And now let's say that I'm gonna create a variable. It's called x, and x equal minus 27, and we're gonna say that that variable is a float equal 27. And now we're gonna say right here, after that we're gonna set x equal POW of whatever value of x, and we're gonna get the 1/3, so that's 1/3, oops, 1.0 over 3.0, and we're gonna do, that's gonna be the 1/3 cubic root. And let's see, anything else we're gonna send to print. That's all. Serial print x. Now here is the story. Be careful with this. If that x is negative, let's see what happened. We're gonna watch that in the serial monitor right there. Start simulation, and that's what you're gonna get. None, meaning that it was not calculated. So you get a none value, meaning a non value. It cannot do it because it's a negative here. You can certainly do it. Like for example, if you are taking the 1/3 cubic root of this number, then it's as easy. You will have, stop here for a second, and you will have to say, like for example, in the case if the value you are looking at, x, is less than 0, then just make a positive value, x equal ABS of x, and that will do the trick. And you calculate what you have to calculate, and then after that, you know that that result, the final result of that value of x, will have to be negative, and then you put negative back again, and you end up the if. Let me open here something that I'm missing. You open this, and you finish with this, and you finish with that bracket. You print it, and this is for the void, and you're done. So that's basically one way to do with that. So let's see. Now you end up with a -3, which is the correct answer. See? So that's the only thing that you want to be careful with the POW. And no more into it. Let's get this. There's nothing more. For whoever wants to copy it. gonna copy it, and I'm not sure now, it would not fit on the comment section. It would not fit, so I'm gonna leave it there. As always, have fun, whatever be your final destination. Bye.